Hello. Excuse my terribly creepy intro. If you're ever curious about what my hair looks like whenever I wear a hat and I take the hat off, it's this. So there you go. There's a little fun surprise for you. Anyway, welcome to either Monday or Tuesday, whatever day this is for you, watching this video. Normally on these days, I give you a pre-made lecture from someone else. No, not today. We're going to get a lecture from yours truly on electron configuration because let's be honest, this stuff can be tricky. It can be confusing. So we're going to knock it out together today. So here's what I'm going to do. I'm going to get this loaded up on my other screen here. Wow, I'm woefully underprepared. Okay, share my screen. Microsoft Whiteboard. Yeehaw. So y'all see my whiteboard. I'm going to pull it over to this homepage. Oh no, it paused my sharing. Resume. Sharing. Excelente. Boom. Yes, that's what I want. Okay, great. Awesome. Now I need to set my whiteboard settings to be on this screen. Perfect, we're good to go. Okay. Today, if you are my first, third, fifth, seventh hour, you'll be watching this on Tuesday. If you're second, fourth hour, you'll be watching this on Monday. Either way, I'm going to go fairly fast because it's a pre-recorded video, right? You can pause, you can rewind, you can slow it down, whatever. Also, these definitions I have pre-written today, right? I'm not going to be writing them out. So that'll also speed us up a little bit. So what I need you to make sure you do is if you need to write these definitions down, you're going to pause, okay? I'm not going to be waiting for you to write those down. You guys have the option to pause if you need to. Okay. Let's dive into it. What is electron configuration? Basically, we know electrons orbit or exist around the nucleus of an atom, and that's kind of at this point all we know. We've looked at Bohr models. We know that how they're arranged a little bit, but they're a little bit crazy in their existence, right? Because electrons are sources of crazy amounts of energy, right? Because they're constantly moving. And so we create these probability clouds to kind of predict where we think they're going to be depending on which electron we're talking about. So what do I mean by that? Last week we talked about the S, P, D, and F blocks of the periodic table. Today we're going to look at those blocks in a respect to the electrons that we find that are in those blocks, right? The final electrons in those blocks, depending on where they're organized, are going to have different shapes. So first thing that you need to be writing down today is that orbitals are the probable location of an electron. The shape of that probability cloud will change depending on which electron or energy level you're looking at. Well, what do I mean by that? Well, first things first, hooray. Microsoft Whiteboard has updated and I now get purple. Purple is one of my favorite colors to write in and one of my favorite colors in general. So now I'm going to be using purple all the time. So let's look at what I mean by that. Over here, we have this little table full of orbital shapes, okay? So this is the orbital shape for any electron found in that S block. What do I mean by that? Well, our S block we know is groups 1A and 2A. The last electron for lithium or beryllium or these electrons in 1A and 2A will have this probability cloud that looks like that. That's the shape. No, I don't want you to have crazy in-depth memorization of these shapes, but I want you to be aware of what we're looking at. Now, so those would be your S block elements. Here's your P block shapes. If you notice, we now have more possible shapes, and the more and more we get, the more complex we get. So this is talking about the P orbital, right? Those would be your groups 3A through 8A elements, if you remember back, but they can have up to 3 possible shapes. These are all often called dumbbell shapes, but now there's 3 dimensions, the X, Y, and Z axis. And so that dumbbell shape, whether it's around the Y axis, X axis, or Z axis, that's for those P orbitals. And moving on to the D orbitals, those middle block elements, those transition elements, we can have 5 different shapes. We're getting larger and larger as we go on. And the shapes can get crazier and crazier. Look at this one, right? And these are really cool and important things to recognize here. These P-1, P0, P1, because those are directly tying to the quantum numbers, which we talked about last week with the quantum numbers of a certain atom. We're going to talk about more on Wednesday, those quantum numbers. But I want you to be aware that within those orbitals, right, they're within that P block. Let's ooh, wow, yikes. Let's look at that P block, okay? Let's look at that P block right here. This is our P block, as we know, right? If my you can see right here, those are your p block elements. Now within those p block elements, let's look at per energy level or per period, how many electrons or how many atoms are there in there? Well, there's 1, 2, 3, 4, 5, 6. The direct corresponding possibility for how many different shapes in that block is just half of the number of electrons, because what we're going to learn later is that there are 2 electrons found in each of these shapes, right? So if we have 1, 2, 3 different shapes or 3 different probabilities or 3 different orbitals within the p block, each one can contain up to 2 electrons. There's your 6 electrons for those 6 possible in that p block. It'll start making sense the more we look and the more we dive in. And then finally, the f block elements. We don't deal too much with f block elements, but we need to know they're there. Wow, I cannot write an F and not, there we go. The f block orbitals get crazy, right? The more and more electrons we have and the larger these clouds get, the crazier they get. And if you notice, 5 of these, right? 5 different shapes, or not 5. What am I saying? 7 different shapes, because there are 14 different atoms found in the F block. And for D, it's the same 5 different shapes because there are 10 different atoms found in each energy level of the D block. So those are orbital shapes, recognizing them. And these quantum numbers here, right? That L quantum number, or no, that would be M sub L. That would be your M sub L quantum number, which we'll talk about again more in your video tomorrow. Or Wednesday for if you are watching this on Monday. So that's orbital shapes, recognizing that there are different shapes depending on which electron is found where in which group. And so all these electrons are orbiting around the nucleus in these crazy different shapes. We just need to recognize them and understand that. I know I don't need you right now to have those memorized. We're going to talk more about that in a second. Okay. So orbitals, the probable location of an electron, shape of probability looking like what we just looked at. Let's move on from orbitals. Let's talk about this term called the Aufbau principle. We're going to be operating mostly out of chapter 5.3 for this thing. So if you want a chapter to look back in your book, 5.3 is a great place to look. But the Aufbau principle states that each electron occupies the lowest energy orbital available. And so fill the Aufbau diagram with increasing energy. So what do I mean by that? Well, let's jump down here to an Aufbau diagram, okay? Aufbau diagrams are these things right here. Please ignore anything around it, but this right here is what's called an Aufbau diagram. Because what the Aufbau diagram does is it breaks down each orbital and energy level and puts it in increasing energy. So you have your 1s energy level, then your 2s, 2p, 3s, 3p, 3d, and you see that it directly increases as our energy increases. So let's identify this on a periodic table. What would be your 1s electrons or your 1s atoms? Well, that would be 1s1. That would be 1s2, because remember helium tags over in the s block and it's technically part of the s block. And then your 2s electrons, that would be 2s1, that would be 2s2. And then continuing on, then we get our p orbital block, right? So you see we have our principal quantum number, that's just the row that we're in, right? And then the orbital or the block that we're in, so it's 2s. And then for that exponent, whether it's 1 or 2, well, which position is it in? Oh, it's our first one, so that's 2s1. Then you have 2s2, and then 2p1, 2p2, 2p3, 4, 5, 6, etc. Okay, and then when you'd come down here, remember that there's that tricky rule that this the D block elements, even though it's in quantum energy level 4, we technically call them the third D block element. So that would be 3D1, 3D2, 3D3, etc. Okay, so what the Aufbau diagram does, or it represents or organizes those orbitals based off of increasing energy. So the more electrons you add, the more energy you get in an atom. That makes sense. Fast moving kinetic energy translates into energy that can be quantized or put into photons. We'll talk about that more once we get into light and the electromagnetic spectrum next unit. But I need you guys to recognize that the Aufbau principle says that we're always going to start filling at the lowest energy. So we start with these down here. The electrons will go in at the 1s orbital and then going with increasing energy. Now, one thing that's important to notice, you go 2s, then 2p. You don't jump to 3s because, look, 2p is less energy than 3s. So you go 1s, 2s, 2p. So you'll see it often written like this in how you see them filled. That's the order that they fill. 1s, 2s, 2p, 3s, 3p. Oop, that's a mistake right there. right? And the reason that's a mistake is because look, 3s, 3p, what's higher energy? So I shouldn't have done these last two. This isn't organized properly. But the reason 3D doesn't fill before 4s, the reason it goes 3s, 3p is because look, 4s is lower energy than 3D. Even though it's the 3 and you think 3 comes before 4, you have to follow this energy trend. And how we prove that on the periodic table is because remember, this is your 3D group right here, starting with scandium. This is your 4s group. Which one comes before? 4s or 3D? 4s, so that fills first, okay? So jumping back to the off-ball principle, that's what we're looking at, filling with increasing energy. Now, we're gonna talk more about how do we interpret and how do we apply this. We need to recognize more principles. The Pauli exclusion principle states that a maximum of 2 electrons can occupy a single atomic orbital, but only if they have opposite spins. So what I mean by that here is this is an atomic orbital. This 1s, that right here, that line is called an atomic orbital. It can have up to 2 electrons in opposite spin of each other. So what does that look like? It looks like one going up, one going down, right? You cannot have up, up, or up, down, right? I'm sorry, you can have up, down. You cannot have up, up, or down, down. That's not possible because of that Pauli exclusion principle stating that you can have only a maximum of the 2 electrons in a single atomic orbital. So that is improper. If you have up, down, then up, up, can't work. Up, down, up, down. We're going to talk more about how they fill, right? And that leads into this rule called the Hund's rule, right? I know this is a lot of rules, but I promise it'll click in a second for you. It's just all going to click, okay? Hund's rule. Single electrons with the same spin must occupy each energy orbital before having opposite spin occupy that same orbital. So what that means is we all will fill with 1 each individual atomic orbital before we go back and fill with 2. Each one of those little lines or atomic orbitals can have up to 2, but we can't put them both in at the same time. If you only have 2, you have to go first, then second, then third, then you'd come back to 1, 2, 3 if you had more. So incorrect would be here, having 2 in the filled orbital before you have any in the others. That's Hund's rule. You always fill individually first. So let's practice this. I know that I just threw a lot at you. So if you are confused and you need a second, rewind back, watch it over again, then join us here. Okay, so I'm going to give you that second. Wow, I just am moving everything all over the place. So let's do some off-bod diagram practice, filling in off-bod diagrams for certain atoms. Now, to do so, I want to be looking at the periodic table, and let's do a super simple one first, right? Let's do helium, okay? Helium right here is in which principal energy level? It's in N equals 1, okay? It's in which block? Technically, helium is an S block element over there. Okay, so in which element is it in that block? It's the second element in that 1s block. So it would be 1s2 is how we would identify that. So let's fill in that. Okay, let's look here at the off-bod diagram. If we have 2 electrons, because helium, when it's neutral, has 2 electrons because of its atomic number, right? If we have 2 electrons, they first go, and they apply here, they go up and then down. And you've just completed an off-bod diagram for an atom of helium. Very simple, right? If it looked like this, it would be incorrect because of Hund's rule, right? Or if it looked like that, it would be incorrect, not because of Hund's rule, because of the Pauli exclusion principle, okay? So it must be 1 electron going up in that direction and then 1 going down. So to bring it all back together, what that means is whenever we look at the orbitals for helium, it has 2 electrons that both exist with this circular shape. One of them spins one direction while the other spins another, okay? So they're spinning in opposite directions. That's what that up and down spin means, right? So that's what we're identifying within those orbitals and within those atoms. That's helium, super simple. Let's make it a little bit more complex. Let's go lithium, still very simple. So what do I know about lithium? Lithium is atom 3, okay? So it has 3 electrons when it's neutral. So I want to be contributing 3 electrons to this off-bod diagram. Now, I know I can go here, 1, 2, then where do I go? Do I jump to P or do I go to S? I go to the lowest energy level possible, which here is 2S. So it's, boom, That's it. Those are 3 electrons. 1, 2, 3. They're all contributed. They're all applied. So we have completed an Aufbau diagram for lithium. Very simple. Now, the way that you would write out the electron configuration of lithium would just be 1s2, 2s1. If I were to ask you, write the electron configuration for lithium, that would be it right there, right? Because what you've done is you've just identified and showed me those simple, you've showed me those simple applications of where our electrons go, okay? 1s2, 2s1, okay? Now, one other really important thing to know is that's called long form notation. When you write out everything, that's called long form notation. There is what's called short form notation, which basically takes it's a shortcut of writing these long values. So we're going to get into that with this next one. But the one that I want us to identify here is, let's do fluorine. Okay, fluorine is element number 9. Okay, so I'm going to come down here, fluorine, element 9. Okay, so how many electrons? 9 electrons. So let's apply 1, 2, 3, 4. See how I did that? 1 up, 1 down. And now I can go 1, 2, 3. Okay, so if you notice, I didn't apply those 3 and I didn't go 1, 2, 3, 4, 5, right? I'm applying those 5 electrons that we find in the P, following Hund's rule, going 1, 2, 3, 4, 5. Now I've written in 9 electrons, so I have a completed Aufbau diagram for fluorine. Now let's write its electron configuration. All you do is, how many 1s electrons do you have? 1s2, 2s2, 2p5. Okay, that would be the electron configuration for fluorine. All I'm doing is I'm taking that Aufbau diagram, writing it out with what I know. 5 electrons in the 2p orbital. Boom, perfect, awesome. So shorthand notation. What we just wrote was 1s2, 2s2, 2p5. Okay, I don't know why I just erased all that. That was silly of me. Okay, so that's what that looked like for fluorine. Now, there's a shorter way of writing that. It's not much shorter, but I want to teach it to you. Fluorine, right here, whoop, jumping up here. Fluorine is here, right? So is there a way, is there a full energy level before fluorine? Yes, there is a full entire energy level. That 1s energy level is completely full. Whenever it's full, it has the configuration of helium because that's its noble gas right there. So if you're in the 2nd energy level, you can encompass everything that came before it by writing what's called shorthand notation. And this was in your, what was this in? This was in your Admentum, so this shouldn't be new, but you'll see it written like this, helium, and then 2p5. Because what did that just tell us? That just told us that helium, we just wrote out, had that, oh shoot, I messed up. Geez, and I'm not going to edit this, so I'm just going to go back over. It's not helium 2p5. It's helium 2s2 2p5. Because what that helium takes place of is that 1s2, because what's the electron configuration of helium? It's 1s2. So right now it doesn't seem like a huge shortcut, but when you do these atoms that have much more electrons, it's a huge shortcut being able to represent those numbers by just a single atom written in brackets, okay? So let's do another just to get these more and more familiar, okay? Let's do magnesium, okay? Element 12. Magnesium is element 12, so I know I'm gonna have 12 electrons to contribute. I can go the long way, which is just going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Perfect. Aufbau diagram is complete. If I write this out, this is 1s2, 2s2, 2p6, 3s2. That is the electron configuration for magnesium. Now, shorthand notation, making it simpler. Is there something that has 1s2, 2s2, 2p6 configuration? Well, let's see. Magnesium's right here. What's its nearest full noble gas? Neon. Great. So I'm going to use neon because that would be encompassing all those that came before it. Neon 3s2, because what you're basically saying is that those 3 values are the configuration of neon, right? So you can just put neon 3s2. Much shorter, much simpler. Starting to make sense a little bit, okay? Let's do a D block element. Let's do a D block element. So I'm going to come back here, And yes, it's just practice, 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 okay? So pause this. If you want to try and do it on your own, pause it and come back and see if you did it right. So the D block element, let's take vanadium, okay? Vanadium is atom 23. So we know there's 23 electrons. So we know we need to put those in our Aufbau diagram. So for vanadium, 23, let's put them in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now, I'm jumping to 4s2, not 3d3. Why? 4s2 has less energy than 3d2, right? It's lower on the scale. So then I go from here, I jump to 4s2, right? I lost track of how many I just applied, but I think it's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 21, 22, 23. Vanadium, writing it out in long form, would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, because I'm just going from bottom to top, writing it out. Now, that's correct. That's just a lot to write. So this is where shorthand notation gets really, really helpful, right? So let's find vanadium. What's its nearest filled noble gas? Argon, element 18. So that'll knock out 18 electrons if we just go argon. And then after argon, we still have 4s2, 3d3. So we have to make sure that we go argon, 4s2, 3d3. So what that basically did is it just encompassed those elements right there and said that's the configuration for argon. I'm just going to write it as argon in brackets and then the rest. That's electron configuration, okay? We're doing it, and it's very complex in nature because it just feels different, right? But one of the things that I really want you to understand is that it's really basic, and you can always check and see if you're right, okay? Well, as long as you're following the Pauli exclusion principle and you're making sure that everything is in opposite direction for an individual atomic orbital, and as long as you're following Hund's rule, that you're filling everything first once and then you're going back and filling everything again, you can just count and double check. Vanadium's element 23, if you have 23 here and you've organized them correctly, you've probably done a proper Aufbau diagram. Now, the unfortunate thing is there's not a great way for me to ask you to fill out Aufbau diagrams, so I may be asking you on your quiz to take a picture of you filling out an Aufbau diagram, okay? So that is electron configuration, Aufbau diagrams. If you need more practice, hit me up. I've got so much. I can set up a Zoom with you for Wednesday, right? We have that whole block. I can explain this in depth with you. So if you are watching this on Monday or Tuesday and you're like, this makes no sense, first, watch it again, because I guarantee you the second time it's going to feel a little bit more familiar. And then if you're still feeling super scared, let me know. Because the one thing that I didn't talk about too much is these quantum numbers. We talked about that on our video on Thursday and Friday. So that'll be tomorrow's video, talking about those quantum numbers, okay? Because we first have to understand electron configuration, then we can talk quantum numbers, okay? Cool. I know that's a lot, but that's all I got for you today. I'll see you, you're either watching this Monday or Tuesday. I'll see you Thursday or Friday. Peace.